Hello viewers, welcome to another section of my tutorial, and today we have a question in applied electricity, and it says we should find the current in the 10 ohm resistor in the circuit shown below using the Norton's theorem. So we have a 10 volt supply here with in series with these 12 ohms, and this 10 ohm being part of the circuit. So you are supposed to find the current through this 10 ohms alone using the Norton's theorem. So in the Norton's theorem, we need the Norton's current as well as the Norton resistance. Where the Norton's current, we are going to replace the 10 ohm or the resistor in which we want to find the current through with a short circuit, and that short circuit should have the Norton's current IN. So after we find the Norton's resistance across the open circuit where the load resistor or where the resistor you want to find the current through is. So let's start by replacing the 10 ohm resistor with the Norton's current IN. So after redrawing the circuit, we have IN replacing the 10 ohms, then we have our 4 ohms here, we have our 2 ohms here, then we have the 10 volts as well as the 12 ohms, the 8 ohms and the 6 ohms. So right now we have replaced the 10 ohms with the Norton's current IN. So what you're going to do is that you have to find the value for the Norton's current IN. So we can do this several ways. So we can apply the Kirchhoff's rules here to find the current IN. It's a simple Kirchhoff's rule. So you represent here with I, that is the current I coming from the source. You also represent this side with the current I1. This side is going to be current I2. So after finding this, you know that if I1 is moving this place, it will split into this IN, and it will also split to this part, where this part is I1 minus IN. Nicely like this. So after when you come here, you know that I2 is coming. It will come and meet IN here, and the two will move as I2 plus IN. So once you have this here, our goal is to find the value for IN. So what do? You take a loop, and in the loop you sum all the voltage drops to be equal to the voltage source you are having in that loop. So let's first take this loop from here. You take this complete loop here around here. So we are going to have the source, which is 10 volts, to be equal to, so to move, so this is a voltage drop, that is 2 ohms by I1 plus 4 ohms by I1 minus IN, then plus these 12 ohms. So the total current I will be the current that will pass through the 12 ohms here. So plus 12 multiplying I. Nicely. So after, let's make our expansion and simplify. So you have 10 to be equal to 2I1 plus 4I1 minus 4IN plus 12. I is the same as I1 plus I2, because I splitted into I1 and I2 here. So once you get this, you come down, you write your 10 should be equal to, here will be 12I plus 12I2. So 12I1 plus 2I1 will give us 14I1 plus 4I1 again. You are going to get 18I1. So plus 12I2 minus 4IN. Nicely. So once you have this, we simply make it equation 1. Then we come to our second loop. We take this side down here as a complete loop, this as a complete loop. So we also have another 10 is equal to 6I2 here, 6I2 plus, so from here the current passing through here, so you have 8I open brackets 8I2 plus IN. Nicely. Then finally plus the 12 ohms here, where the current passing through is I. So we expand this and we get 10 is equal to 6i2 plus 8i2 plus 8in plus 12i. So from here we get 10 to be equal to this plus this will give us 14i2 plus here when I split I'm going to get 12i1 plus 12i2. So I'm going to get 26i2 plus 12i1 plus 8in. So when I reach here, I'll make this equation 2. And finally, I'm going to take this loop here as my third loop. And that one, I'll get 2i1. Here, the voltage drop is 0 since there is no resistance here. It's a short circuit. So I'll get 2i1. When I come down here, you see that i2 is coming down. So taking this loop, it will be against it. So you get 2i1 minus 6i2 to give me 0 as equation 3. You simply punch this into your calculator and you get the values for I1, I2 as well as your IN. So from simplification you get IN to be equal to 5 over 97. That is going to be your IN, 5 over 97 amperes. So once you get this, you move straight to finding the Norton's resistance, that is the Rn. Then you move ahead to find the current through the 10 ohms. So how do you find the Norton's resistance? To find the Norton's resistance, what we are going to do is that we are going to find an open circuit. So where we had the 10 ohms, we are going to open it up and put the Rn there. So let's redraw. So we are going to have another diagram again. So after you make an open circuit here, that will be your Rn. So you come down. So here will be our 10 volts. Here is our 4 ohms, 2 ohms. Here is our 6 ohms, and here is 8 ohms. So right now we have redrawn our circuit and we have replaced where the 10 ohms with our open circuit Rn. This will be the Norton's resistance. So we have to find the total resistance across this open terminal. So what we are going to do is that we are going to open this wide so that you find the effective resistance across the two terminals. So it should look like something where you have one terminal here, then the entire circuit in between, and another terminal here nicely. So how do we do that? So assuming if you are to open this here, then we move this one here, what you're going to get is that you see that you have to label this as A, B, C, and D. So from here, when you open from this here, you get A to B, B to D, D to C, and C to A. Then as well as B to C, B to C here. So you get from here to here, from here to here, from here to here, as well as from here to here. So let's see how when we expand it's going to be. So we make our A here, where A will be an open terminal here. So when we have our this A, you will quickly move this being a terminal here. So let me draw it here. So we have the terminal like this. So after we move up, so here will be our A. So once we move up, we move up. So once you are having this A, I'm going this way, A to C. There's a resistor there, and that is a 4 ohm resistor. So I'll make my here as C, and that is a joint here. From C, we have from C to D. So what do? I have another resistor, and that is, here is my 4 ohm, and here will be my 8 ohms. So up to D here. Then from D, I have from D to B. So we know that from A to D, that is our A to D, that is where the terminals is. So D will contain the second terminal. So D will come somewhere here. So that's our D. So once we have our D here, then we come down here, we have A to B here. So A will also come down, like from here to here. So from this terminal, it was divided into A to C and A to B. So coming, we have our A to B here nicely, and that is 2 ohms. So once you have our 2 ohms, we move from B to D, that is 6 ohms, to D, here is 6 ohms. Then finally from B to C, we have our 12 ohm here. So B to C, that will be our 12 ohms. So this is the resistors which has been placed within the terminals A and D. Now let's move ahead to find our Rn, that is the total resistance between these two terminals. So from here we are going to apply the delta star transformation, since this and this and this and this are neither in parallel nor in series. So what do? We introduce a star connection, another star, then we have this. So we label here as A, here as B, here as C. Then now what will be the values for A, B, and C respectively? You know that A is in between 4 ohms and 12 ohms, and the entire delta is 4 ohms, 12 ohms, and 2 ohms. So for the transformation, you realize that A is going to be 4 times 12 all over 4 plus 12 plus the 2 ohm here, and that will give us 48 over 18. And what is that? 48 over 18. So we get 8 out of 3 ohms. That will be our value for A. Then the value for B is going to be, B is in between 4 ohms and the 2 ohms. So we get 4 times 2 all over 4 plus 2 plus 12. And this will give me 8 over 18. And this is equal to 4 over 9 ohms. And finally the C will be equal to 2 times 12 over 4 plus 2 plus 12, and that will be 24 over 18, which will also be equal to, that one too will be equal to 4 over 3 ohms. So redrawing this, we are going to have our circuit to be this way, then finally this way, finally this way, then this way nicely. So here being our B, you have 4 over 9 ohms here, you have our A 8 over 3 ohms, and we have our C 4 over 3 ohms. Here is 6 ohms here is 8 ohms here, and here is the A and the D. So after this, we have to find the effective resistance. So here and here are now in series, this place and this place are also in series. So what do? We just combine them. So we are going to have this place combined with this place combined with this place. So our next drawing will be somehow like this, moving up, then something like this. So here will be our D, here will be our A. So what will be the, here is 4 over 9 ohms. This place will be the combined 8 over 3 plus 8, 8 over 3 plus 8, and that will give us 32 on 3. And the down one is going to be 4. This place will be 4 over 3 plus 6, and that will give us 22 on 3 ohms. So from here, we know that this and this are now in parallel, since there is a node here, and when you traverse through that path, you are not going to meet any other elements. So what do? We find the parallel, and it's going to give us 32 on 3. So this place and this place, we have 32 on 3 being parallel to 22 on 3, and that will give us 32 on 3 multiplying 22 on 3. You punch it onto your calculator, 32 on 3 plus 22 on 3, and that will give us 352 over 81 ohms. So finally our resistance becomes this in series with this, where we have this to be 4 over 9, and here will be 352 over 81 ohms. So we simply add them to get our total resistance. So 4 over 9 plus 352 points. So 4 over 9 ohms plus 352 over 81 ohms, and this is simply equal to 388 over 81 ohm, which is also equal to 4.8 ohms. So we have finally got our Rn, and once you get your Rn, you know that to find the current. So our I, so assuming you are having the Norton circuit, we having something like our In will be here in parallel to the Rn, then also in parallel to the resistor we want, and that is the 10 ohms. So we use current division to get the value for the current through this, because the In was split and some will pass through the Rn and some will pass through here. So we need this current I passing through the 10. So our current I will simply be equal to the Rn using the current division rule over Rn plus R multiplied by the In, and this simply equal to, that is 4.8 over 4.8 plus 10 multiplied by our Rn, which we had 5 over 97 here. And what are you getting? So 4.8 all over 4.8 plus 10 times 5 on 97. Now give me 0.0167 amperes. So this is finally the current through the 10 ohm resistor, as you have gone through all the process stepwise. Thank you. Kindly subscribe and share if you find this helpful.